Fellow mathematicians, puzzlers, and other curious people, when you have a formula, it can be pretty easy to plug in some input values and calculate some output values. But what about when you don't have the formula, when you just have some data to try to figure out a formula from? Let's take a look at some examples. So in this example, we have some x values and some y values. Usually x is your input and y is your output. And I see here that our x values are integers that run from -1 to 5, and our y values seem to be whole numbers, 2, 3, 4, and 5. Now we're not given all of the outputs, so it's a good idea to try to calculate those, but to calculate those, we would want to come up with a formula to make sure that we're working accurately instead of just guessing wildly. So I notice that as x increases by 1, y also increases by 1, so there's a fixed distance between x and y. So that tells me that y equals some number plus x. So in other words, we could say that verbally as our output is some fixed amount more than the input. Well, what amount is that though? Well, one thing I notice is that when our input is 0, our output is 3. So that tells me our output must actually be 3 more than the input. So our rule here can be that y equals 3 plus x. Then it's very easy to go ahead and calculate the rest of the y values. 3 plus 3 is 6, 3 plus 4 is 7, and 3 plus 5 is 8. Now we can plot these on the graph at -1, 2, that's 1 backward and 2 up, 0, 3, neither direction forward or backward, 3 up, 1, 4, 1 forward, 4 up, 2, 5, 3, 6, 4, 7, and the next is off the chart. But it would also be possible to have used fractional values and values outside that range, and we know of no reason to suspect that the pattern would do something different. So what we can do is just go ahead and draw a line, and since we have no specific reason to believe it stops in either direction, we can put arrows on the end, and that is how we describe this pattern using a formula, a verbal description, and a graph to illustrate it. Now, not all patterns are quite this easy to figure out. So here's another one. We have the same range of x values, but our y values seem to be doing something different. They're not a fixed distance. In fact, these two y values here are exactly the same as the input values. So for these, it would be tempting to say that y equals x. But then we quickly see that that's not true, because 4 is not 2, but also 1 is not -1. So what's going on here? This is down to experience to notice this quickly. One thing you might notice is that the outputs are the squares of the inputs. If you've recently done some calculations with squares, that might be fresh in your mind. For example, that 2 times 2 is 4, and 4 times 4 is 16. The outputs, we could say, are squared inputs, and we can write that as a formula by saying that y equals x squared, and we can graph that out the same way as the other. We can say -1, 1, 0, 0, 1, 1, 2, 4. Let's see, 3 times 3 is 9. Well, that's off the table. 4, 16. Again, that's up off the edge. 5 times 5 is 25. So we get this sort of looped shape. Well, that's a little wobbly, but you can see what it's doing. And so that is how you can be a formula detective and come up with a formula that fits a data set that you're given. And then you can use that formula to finish out some further outputs from your data set, and you can illustrate that data set using a graph. Calculator!